go on my talk. So this is stable space-time finite element method for parabolic equations. And this is from this article that I wrote some time ago already, some years ago, but I used FreeFM for this. And quickly, so for time discretization of PDEs, with the popular methods are usually vertical methods of lines, also the horizontal methods of lines. And then we have time discontinuous Galerkin schemes. We have P and HP time stepping schemes from Babushka and Janik. These are very known papers. But for this particular work, we take the time variable as just another variable in space. Okay, so we consider time as a spatial dimension. So I take you through the model problem, and then I explain some of the basic ideas. So if you have a typical heat equation like this, the derivative of T, or if you have a heat equation like this, then we consider a space-time domain. Particularly, you can do this for a moving space-time domain, where this is a Laplace operator, and then we have also the partial time derivative. You have a given source function f, and you have your sigma to be the boundary, and then sigma of 0 to be the initial boundary condition, initial condition, and then you have your, of course, there's a sigma t, which is also I consider as the final time simulation. So your boundary, the whole boundary is defined by the sigma of sigma, and then sigma of 0 and sigma of t. And if you do a variational formulation of such a problem, what you do is you multiply by some test function. And then in this case, we use an anisotropic Sobolev space. So this kind of anisotropic Sobolev space where we do an integration by part in time. If you take your model problem, if you take this problem and you multiply by the test function V, then you can do an integration by part in time for the first part, and then an integration by part in space for the second term, for the second equation. And then if you do that, you get a bilinear form that looks like this, okay? And so a variational formulation, we say that find U in an H1, 0 and 0, 0 of Q, such that your AUV is equal to LV for all V in H1, 1 and 0, 0. And by this, I mean, if I say H1 or HS and ST, I mean that you have an anisotropic Sobolev space where you have U is square integrable, and then you have derivative in space, and then you have some derivative in time as well. And this will take care of the derivative in time and then the derivative in space in this case. But we want to do a discrete formulation of such a problem. This is so we go on to do talk about a discrete variational formulation. So just means that if you have your space-time domain looking like the one on the right, where you see your space-time domain, which is omega on the boundaries to the left and right, and then you see the initial condition, which is sigma 0, and then the final condition, which is sigma of t. And then if you discretize, you have elements, and then we in this particular case we consider elements. We consider interfaces as well, interior facets of the elements. So for each two elements, we also consider the normal outward unit normal vectors in space and in time. Okay. And then we go through, we try to give some formulation for the quasi-uniform mesh, and then a discrete space setting, which is VH, which is continuous, and then every VH is P of degree P, discrete polynomial of degree P on each element. And then with this, we define a discrete space-time space, which is V0H, which is VH as we have it here as well. And then for, as I described, for each element, each two elements, we consider an interface, an interior facet, and then an adjoining outward normal. So you can see that with such a problem, if you have a moving domain, it's possible to formulate this problem in a setting where you take a test function WH, which is a linear combination of VH and then the derivative in time of VH, and scaled by the mesh and then a parameter theta. And the idea is that this is this gives you an idea of where you are trying to use kind of a like an upwind idea to solve this kind of problem. So this is what we do. So you start with your model problem again, your Higgs equation, and then you multiply through by your test function. But now you should bear in mind that your test function is a linear combination of VH and then a scaled, the mesh scale size of the derivative in time of VH as well. If you do that and then you multiply through it, you see that you have here, I do not do anything to it for the time derivative part, but for the spatial derivative part, if I bring in the test function, then you see that we have a Laplace of U of VH, and then we have the theta H, and then the Laplace of U of delta of T of VH, which is the time derivative of VH as well. So to do the formulation, what I do is that first I take a second term in this equation 7. I take the second term, and then I do a spatial integration by parts in space. So if I do an integration by parts in space, then I get this part. I get this part, this term here, which is coming from the boundary. And then I use the idea that the normal derivative in time, in space, the unit derivative in space on the initial and then on the final time are all 0. And if I do that, and then because of the fact that my test function is coming from a V0H space, then it means that all the other parts of the boundary condition or of the boundary terms are all going to 0. So this whole part goes to 0. And then I'm left with this term here, which is the derivative in time of U VWH plus parts where we have done the integration by parts, and then this term here, which has a Laplacian in space, and then a derivative in time of the test function. So this is the term that a bit one must work on actually. So to do that, we do a summation on the elements. We go now onto the element wise. So on each element, we do a sum over all the elements. Because of how I defined my my space, my discrete space to be C0 functions, or there should be at least C0, we try to implement this idea here, because other than that, then you need more, you need elements which have higher derivatives. So here, if I do this, then I apply again integration by parts in space. If I apply integration by parts in space, then I have a sum of all elements, and then over all element interfaces, interior faces, then integration by part, the boundary terms that are coming from this integration by parts in space. And then if I take this, then we use an idea of similar to what you usually do in the discontinuous Galerkin framework, where when you have interfaces or interior facets, you can always do a jump and then a jump and a mean and a jump and a mean in this way, but I define these terms later. So here for the interfaces, we have an interior jump in the space direction, and then we have also this term here, which is coming from the boundary terms, the boundaries basically. And then the next thing is that we take the first term in this equation. So the first term now, what we do is that we do an integration by parts now in time. So first we do an integration by parts in space. Then now we go to the first term and then we do an integration by parts in time. And then if we do an integration by parts in time, then we get also a jump in time, as well as some other conditions also because of the normal, the derivatives, the actual unit normals, which are also in time. So we get this term as well. So the blue term here is coming from doing an integration by parts in time. And then you see that also you have a normal derivative in time. And then you have also the magenta term, which are coming from integration by parts in space, which is the fourth and the fifth term. So as I said earlier on, it's similar to what happens in the DG case, where if you have two functions, scalar, you have the product of two functions where you take the jumps. You can always write it in terms of a mean and a jump plus a mean and a jump of the functions. But if it is in space, you can do the same thing as you do in DG ideas. But if it is in time, then if you have a jump of the two functions in time, then you write it as an upwind term and a jump in time plus a downwind term plus a jump in time. So this is the only difference when you have the jump in time and then the jump in space. So if we do that, then if we take the blue parts, then we can apply the second equation. And then if we the second equation here, and then if we take the magenta part, then we can apply the first part. Okay, the first equation as well. So basically, we take those two terms. So if we go back here, we put these two terms together as this, and then I apply the idea that I just said. So take this part, apply the other inequality here, and then take this part, apply this equality, and then expand it. If you expand it, some of the terms go to zero because of the usual idea that the jump in space, this jump in the spatial derivatives are zero, and then also in the time derivatives are zero. So this is well known. Then some of the terms on the boundary, we realize that also becomes zero because if we have the terms on the boundary, then the derivative, the spatial derivative of u, and then multiply by this term here gives us a zero. So we have also a lot of the terms as well going to zero. And then what we realize that if you have such a scheme, you add a consistent term. So that's why I said this. We borrow these ideas from discontinuous Galerkin. But now we add this consistent term, and then once we add this consistent term, we are able to have a variational scheme, a discrete scheme in this setting, where our bilinear form is now given by this equation number 10, which consists of several parts. both the upward terms, the jumps, and then the means as well. And we also have the consistent term, and then a penalizing term, which is the delta. So if we do that, then the next idea is that we want to show for coercivity results. So for coercivity results, we need a discrete space where we're able to do we're able to show for a coercivity in this space. So we have this discrete norm here, and then of course for coercivity results you need ideas from your inverse inequalities, your scaled trace inequalities as well. So if you do that, what you then see is that you can write a coercivity result for this bilinear form that we have, okay, or for this discrete variational scheme that we have just described. And then if you do that, you have a coercivity result based on the theta that you choose should be positive, should be greater than 0. And then it be sufficiently small such that it is actually bounded by the inverse inequality, the constants from the inverse inequality, and then the quasi-uniform inequality as well, the inverse of it. And then our bilinear form is actually coercive with respect to the space or the norm that we have described here, the discrete norm here. So this is a discrete space-time norm. And then the proof of such an idea follows usual techniques or usual proof ideas from both the parabolic side and also for the elliptic idea. So if you take your UH to be VH, and then you substitute it in, and then you apply Gauss theorem. So if you do that, you have this inequality here. If you make this substitution, you get this equality, and then you have to consider the phases, the boundary terms. So this is the boundary condition, the boundary terms, sigma 0 and sigma of t, and then also all the interior facets as well, And then if you apply this idea, you see that you have the first part here, which is the equality. We're able to write this part, the first term here, which is all the boundary terms, which is the derivative in Q. If you have the derivative in the boundary terms of your domain, then what happens is that a lot of the terms are going away apart from what you have on the final time, which is the sigma of t, and then you also have the other terms here, here, and here are all also present. Then the next part is that you have you're able to apply some ideas again. So the other idea that you need to get this the product of the upward function and then the jump in time minus half of the jump, the square of the jump in time is equal to this term here. If you apply such an equality and this idea here, you're able to come finally to of the discrete norm that we described, the space-time discrete norm minus this term. So we apply some also as I said, the inverse inequalities and then the quasi-uniform norm, because now we try to find what's to do with this term here. So for this term, we apply the inverse inequalities, and then we use the assumption on the quasi-uniformity of the mesh, and then we're able to derive a bound for it as well for that term. And then finally, we're able to provide this bound, the coercivity bound as well for bilinear form. Of course, once you do that, once you have coercivity, then the next step is to provide an idea for boundedness. So for boundedness, we also, once you have boundedness, we have this boundedness form here. We go through the same thing, but now you have the boundedness, you use a different norm for the boundedness as well. So the next steps is to provide some estimates for the projection operator. The interpolant, we use an interpolant which is well known already. And then with this, if we have, of course, initially when I started, I did everything. I showed to you that you can formulate already in a Sobolev space, which is like an anisotropic Sobolev setting. But you can actually, but in this settings of the interpolant, what we do is actually to consider an HS where we assume that the S are the same for both space and time. And then with that, we're able to, we have this interpolant, this estimates on the element basis that you're able to derive exactly this kind of estimate, which is the CS of HS minus the L, and then your V of HS of Q, where S is between 2 and P plus 1. P is the degree of the polynomial, and then S, we said that is greater than the dimension plus 1 over 2. Your L is between 0 and S inclusive. So
sorry, just a remark, you have just 5 minutes more, no more.
Yes,
please.
Yes, please. All right. So to derive some estimates, what you usually do is you have to show some estimates for a priori estimates. What you have to show is basically to show that the terms, the time derivative terms or the jump terms, you have to show that they give you the optimal convergence rates for both the time, the upwind, and then the space parts. So this lemma here describes this idea. And then we need the estimate as well for the discrete norms. So for the discrete norm we described, we're able to show that actually your discrete norm still also you're able to provide optimal rates for the discrete norm in this setting. And then with this idea, you're able to show the a priori error estimates for this scheme, scheme that I just described. And all this, I did all this implementation using FreeFEM, I should say. So the numerical results I show you here are all done in FreeFEM. This for I think the new version that the latest version that was sent. I installed it yesterday, and then my FreeFEM now has crashed. So I don't know what happened. From the latest version that was installed yesterday. So if you take this is a very simple example. If you take such a very simple example, then you expect to get optimal rates for such a domain for P1 and for P2. And then if you take, this looks interesting because you have 1 minus t and half sine of pi of x. If you take such an example as well, you see that this is really not this solution. This U is a bit in a special space because you do not have the exact you do not have H1 or anything like that, because you have some aspect, a singularity, basically a singularity here in time. And so you do not expect to get rates to the power as you expect because of the singularity. But of course, we know I know how to recover this this singularity as well, and this I also hope to implement again in FreeFM. But my system is crashing now. Okay, so basically, this is what I wanted to share. Some of the things that I've also done in FreeFM. And so I've been able to, so far I show you the variational formulation of a stable space-time finite elements. From that you have a heat equation, and then you can be able to use some techniques, but this was really made very easy implementations in FreeFM because of a lot of possibilities that you're able to do, like the jump equations, which are easily to implement in FreeFM, and several terms which are very good to handle in FreeFM. And then I also show you the numerical results. And then the next thing that I intend to do, because now in this setting, you see that I've done, it's a space-time. So what I've done is I've done, you can consider it as a one dimension in space, one dimension in time. Of course, it looks a 2D, but the next step is to actually implement a 2-dimension in space and a 1-dimension in time. So this is a 3D setting, or a 2+1 setting. And this is a bit more challenging than I thought, but this is what I'm trying to implement at the moment. And then also other solvers. So if the system that you get from this kind of equation, this kind of model is non-symmetric. So the idea is that I want to try other types of solvers in FreeFM as well. FreeFM has MOMS, Paradiso, Hyper, and other parallel solvers as well, that I want to now also kind of test these kind of solvers in the setting and see how it also performs. So thank you very much for the time and opportunity to present at FreeFM Days on the 14th edition. Thank you.
So thank you for this presentation.